about it. We've been talking about partial fractions last time, and I wanted to do just one little kind of variation. So there's actually, if you've seen partial fractions before, you may be familiar with a few variations. What we talked about last time is a method which generally works whenever you can factor the bottom into different factors. If you have repeated factors, there's like extra tricks you have to do. And actually, I don't really want to get into that. But there is one extra trick which I do want to get into, and that is the long division. So this is a trick which often works, I will say, with partial fractions. Although this is a more general trick that you can use just by itself sometimes. Long division, I'm referring to long division of polynomials. Maybe this is something that you've done before. I think people do this in high school. I don't know. I will refresh your memory just in case. For example, a typical polynomial long division looks something like, this is just a made-up example here, this divided by this. All right. You can simplify this by doing the long division. So we can, this is, it looks like a fraction, but you can actually divide it. A fraction, of course, represents division. So we can divide it. And you're going to do that just like ordinary long division. I don't know how often you do long division, but it's like I'm going to write it with one of these things, the division thing. And it is the numerator divided by the denominator. And the way we write that in long division is the thing that you are dividing is inside this. So it's this thing. I'm writing the numerator here. 2x cubed plus x squared minus 23x plus 16 being divided by that other thing, and that other thing I write on the outside over here like so, right? This is how we would write this as a division. And now I'm going to do the long division in the way that you would for numbers. Now with numbers, you go like digit by digit. For polynomials, I think of each power of x as if it were a different digit. And so the first thing that I do is divide into this 2x cubed term. And just like in ordinary long division, I look over here and I ask myself, what do I have to multiply this by to make it match in the first digit so that like when I subtract them, that first digit will cancel away. That's how you typically would do ordinary long division for numbers. And the answer in this case is, I want it to say 2x cubed, but it says x squared. I have to multiply this by 2x in order to make it match 2x cubed. So I write 2x up there. I chose 2x because 2x times x squared makes 2x cubed. I want this to match. And then we continue, sort of what you do next in long division is you take this guy up here and multiply it by that, and you write it down here. So I'm going to multiply this thing through by 2x and write it down here and then subtract. So it'll say 2x cubed on the front, that's what I wanted, and then plus the next term is 2x times x, which is 2x squared. And then the third term would be 2x times negative 12, which is negative 24x, like that. And then we subtract. I remember when I was in 4th grade, my teacher had a little long division song about all the different steps. I don't remember the song. She would like dance around and sing it, and everybody thought it was great. I hope you enjoyed that little story from my childhood. Now we subtract from here minus this. So 2x cubed and 2x cubed cancel out. The next one will be x squared minus 2x squared. This gives me negative x squared. It's easy to mess up the signs when you're doing this, but I am subtracting here. X squared minus 2x squared is negative x squared. And then negative 23x minus negative 24x, that would be negative 23x plus 24x. That is plus x. All right? And I have done now one step of the long division. I hope everybody is familiar with this a little bit, or at least following along so far? Any thoughts about that? I hope I didn't mess it up either. Okay, what do we do next? Next, just like ordinary long division, you sort of bring down the next digit. So this thing kind of drops down and becomes part of this. And now I go through and do the same thing again in another step. So again, I look here at the top term in the polynomial, and I try to think about how do I make this match with this? What do I have to multiply this by to make it match with this? And the answer is -1. So the next term up top is -1. And then again, we multiply through. So this time I'm multiplying through this bit by -1, and I write it down here. So it says -x squared minus x plus 12. And then we subtract. The -x squareds go away because I'm subtracting, and then I have plus x minus -x, that is 2x, and then we have 16 minus 12 is 4. All right, and this is actually the end of this long division. You don't continue here because now this term is lesser degree than what we started with here. That means we stop at this point, and that's the remainder. So this up here is called the quotient, and this down here is the remainder. All right? Now, what's the whole point of doing all of this business? It's that you can rewrite what we started with in a, I don't know if it's simpler. I would say it's simplified. But in any case, it's more convenient if you're interested in doing the integral. So that's why we do this at all. So my conclusion would be the original thing that I started with, 2x cubed plus x squared minus 23x plus 16 divided by x squared plus x minus 12. This equals, we just did the division, and the answer, the quotient, actually is 2x minus 1. So it equals 2x minus 1, and then plus the remainder part. And the remainder part is this down here over the original thing you were dividing by. So this is 2x plus 4 divided by the original guy like that. All right. And this is the purpose of doing the long division, is that you can start with this kind of big thing and turn it into this stuff over here. Now, why is this stuff any better? It's because actually this stuff is easier if you are interested in doing the integral. Certainly this and this, the first two parts, are very easy to do the integral of. And the last part is appropriate for doing partial fractions, and that's why we do this whole thing. The thing that we began with is not really appropriate for doing partial fractions because the numerator degree is higher than the denominator, and it's not gonna, the partial fractions is not set up to do that. All right? So the idea here, the reason why we do this at all is to do the integral of a rational function. Remember, rational function means a fraction with a polynomial on the top and the bottom. So to do the integral of a rational function where the numerator degree is greater or equal to the denominator degree, the strategy is do the long division, then partial fractions on the remainder part. And then the entire integral becomes easy to do. I mean, easy after you do all that other stuff, which will take you a few minutes. All right? If the numerator degree is greater than the denominator, you can't do partial fractions directly, but you can do the long division and then do partial fractions. That's the idea. So I got one of these to try. We'll do like the whole integral, and then I got one for you, and then maybe we'll talk about something different. All right, so let's try. How about integral 3x squared plus 18 divided by x squared minus 5x plus 6 dx. All right. So this is an example where the degree on the numerator is greater or equal, it's equal in this case, to the degree on the bottom, all right? And I will just refresh your memory. Partial fractions, I said this last time, partial fracts, sometimes I write that because I sound edgy. Partial fractions only works when the denominator degree is greater. So we cannot do partial fractions directly on this example because the denominator degree is equal to the numerator degree in this case. Partial fractions only works when denominator degree is greater. So I'm going to divide first. And that's the point of the long division trick. After you do the long division, you get that remainder part, and in the remainder part, the numerator degree really is less than the denominator degree. And so you can do partial fractions on that. All right, so we begin by dividing. The thing that goes inside the division sign, like so. 3x plus 18. Now, that one happens to have no x term. Because you have to do this kind of digit by digit, you better insert 0x in the middle, because there will be a step of the division which involves the middle term, even though it's 0 when you start off. It's not going to be 0 as you do the division. It's not going to be 0 forever. All right, and then I am dividing that by x squared minus 5x plus 6. All right. So we got to put something up here. It shall be, I'm looking for something for which, when you multiply x squared, it makes 3x squared. What do you say? What should go up here? Yeah? Yeah, just 3. Here the degrees, the x, the powers on x are the same. So in order to make x squared match up with 3x squared, you just multiply by 3. So I go 3 here. Next step, multiply 3 times that other thing and write it down below. So it shall be 3x squared minus 3 times negative 5x is negative 15x. And then 3 times 6 is 18. That's plus 18, right? And then we subtract. The 3x squareds cancel. In the middle I have 0 minus negative 15, so that's positive 15x. And then the plus 18s also cancel. And I think that's it. This is the end, because what I have here is going to be the remainder. This has now the power is less than what we're dividing by. So this is actually the whole thing. You only have to do one step here. If the degrees are equal, this long division only takes one step. All right, so what that means is that my original integral, 3x squared plus 18 divided by x squared minus 5x plus 6 dx, this actually equals the integral. And now I'm going to write the quotient and the remainder. So the quotient is just 3. So I go just 3 plus the remainder part. The remainder part is 15x over this thing, what I'm dividing by. So the remainder part says 15x divided by x squared minus 5x plus 6. All right, that's the purpose of the long division, is to do this little simplification. I guess, I don't know if it looks much simpler, but it actually is better this way, because we are going to now do the partial fractions, right? So maybe I'll just remind us where these came from. I hope you can tell. This is the quotient, right? And then this whole thing here is the remainder part. All right, and now we can do partial fractions. So now partial fractions on that, just on the second part, right? The 3 by itself, we're just going to leave as a 3 by itself, because when you do the integral, that becomes 3x, and there's no problem there. It's the other thing that requires our attention. 15x over x squared minus 5x plus 6. And I hope everybody remembers how to do the partial fractions. We did this yesterday. You begin by factoring on the bottom, and then you try to split the fraction up. So I'm going to write it 15x over. Factor on the bottom. Can someone tell me what do you get for the factors there? Minus 3 and minus 2. Yeah, excellent. Crushing it, as my buddy Nick would say. All right, x minus 2 and x minus 3. Now I want to, this is how we do the partial fractions. I want to write this as a over x minus 2 plus b over x minus 3, right? And in order to figure out what are the a and the b, we have to add together on the right-hand side with the common denominator. So making the common denominator, I'm just going to have a times x minus 3 over x minus 2, x minus 3, right? That's the common denominator for the first one. And then the second one will be b x minus 2 over the same thing, right? And now if you just read across the numerators and multiply out the, distribute the a's and the b's, it'll say 15x equals ax minus 3a plus bx minus 2b. I'm just reading the numerators there and distributing the a's and the b's. And then if you recall from last time, the next step would be to equate the like coefficients on either side here. On the left side, I have 15x. Actually, on the left, there's no constant term. Usually you have an x term and then a plus an extra constant. So I guess this is just 0. And then on the right, I am going to group these terms. I have a plus b times x, and then also negative 3a minus 2b as the constant part. This is just like we did last time. I hope everybody remembers. Yeah? And then we got, we have to equate the coefficients on either side. So the x coefficients, setting them equal, I say a plus b equals 15. And then setting the constant terms equal, it says minus 3a minus 2b equals 0. And then we solve the system. All right. So I'm always pretty much going to solve this by doing substitution. So in the first line, I'll solve for b maybe. b is 15 minus a. Then plug that into the second line. It'll say minus 3a minus 2 times 15 minus a equals 0. And then do some basic, solving for whatever. So I would distribute the 2 there. Minus 3a minus 30 plus 2a is 0. So this says minus a minus 30 equals 0. A equals negative 30. Can you believe it? I think it's true. All right. And then what about the b? So b is 15 minus a, right? That's what I said at the very beginning. So b is 15 minus a, and a is negative 30. That's 15 minus negative 30, which is 45. All right. These are weird numbers, but it's what I have on my paper, so I feel good about it. Okay, so my partial fraction coefficients are negative 30 and 45, right? So all the way up here, that's what this a and the b are, right? And what that means is this thing right here, we can write as this with the a and the b that we just found. So my original integral then, so our integral is, the integral, we had 3 as the remainder, the quotient part, and then was it plus? Yeah, plus. And then the next part, 15x over whatever, we just did the partial fractions on that, and we ended up with minus 30 over x minus 2 plus 45 over x minus 3. This is the results of doing the partial fractions. And now this is very convenient for just doing the integral across each term. I have 3 parts, I should say dx. I have three things there, and then you just do the integral each time. So the integral 3 is 3x plus the integral of that fraction, negative 30. I will sort of factor the minus 30, and then what remains gives me ln x minus 2. This is always how these go. After doing the partial fractions, you get a bunch of ln's added together. And then the last one is 45 ln x minus 3 plus c. That's it. All right. So this is somewhat long-winded, I suppose, but you know, it's kind of basic steps, although easy to screw it up at any point. The long division followed by the partial fractions. Any questions about the whole procedure here? It'll take you a few minutes, but it's kind of simple tricks. All right, let's try one. I got one for you all. Actually, I had two. So just to make sure everybody is cool with the long division, I had one that's just like purely about doing a long division, and then one which is an integral. So your first job is just do the long division. And I made sort of a big one here. X to the 5 plus 2x to the 4 minus 3x cubed plus x squared minus x plus 4, all divided by x squared minus x plus 1. See what you think. So just do the division for that. I'm not telling you to do the integral. And then here, if you need some more action, here's an integral to do. X to the 4 plus 4x cubed plus x squared plus 3x plus 1 over this business here. All right, see how you feel.
so.
Yeah, I think so. I can write the first few steps of the division, see if you agree.
I didn't finish it, but you agreed so far.
Okay.
You don't like this? Is it different from?
Yes. Yes.
Oh, yeah, 'cause I forgot to bring down.
Mine's not right. I forgot to bring this guy down. And so that should be a 0 here. Is that better?
Yeah, that's good.
No.
Where did the plus?
4 minus -3, plus 7.
Oh, yeah, that's right.
I think that's right. Anybody else agree with my long division? There's many chances to mess it up, and unfortunately, if you mess it up towards the beginning, it totally wrecks the whole thing.
I don't know what
One digit wrong. Yeah, here, -2. So this 4 came from trying to match this coefficient. This should be -3 because it's -2 minus 1. And then you should do one more step.
Yeah.
Oh, that, yeah. The reason for the 4 here is because of that 4. So it should be 2, so actually this should be -3.
That's what we're right now. What's the next one?
Still learning?
Yeah, I just I'm going back to the old example.
Yeah.
When we get the remainder, or when we get the actual answer, and then we do that plus the remainder over the original numerator.
It's the original denominator.
Okay, and then okay. Does that make sense?
Yeah,
Because I was
it should be the denominator.
yeah, I had the denominator as that huge x to the 4th term, so I had no idea how to factor.
Mm-hmm. Yeah, right. That's not possible. I think I wrote it correctly. Yeah. All right, can we talk about, I'm sure we could like do this all day, and it's very easy to make little mistakes. Let's just talk about the integration one. So hopefully you got something like this when you did the long division in the first one. I think that this is correct. My policy is usually like if more than one of you agrees with me, then it's probably right. Like I said, very easy to mess up the details in here, but I think that this is the correct step. Let's try this one all together, and I know you guys have done much of it. So you begin by the division. X to the 4 plus 4 plus x plus 1. All right, and what's my first term in the quotient? I know pretty much everybody started this one off. Can I just call somebody out? How about Taylor? What'd you get for the first?
X squared.
X squared, yeah, right. Because I want to get x to the 4. So now I go through, multiply by x squared, I get x squared plus 2x cubed minus 3x squared. We subtract the x to the 4 is the first term there. That's the whole point of that. We subtract, I get 2x cubed. X squared minus 3x squared is plus 4x squared, like that. And then I drop down the next term, which is 3x. I hope you're with me so far. Next term needs to be 2x. That's so that this x squared times 2x will be 2x cubed. So plus 2x here. 2x cubed plus 4x squared minus 6x. Subtract here. Am I doing all right so far? Yes? No complaints yet. We are going to cancel. Actually, there's sort of like extra cancellation. No problem. We get 3x minus 6x is 9x. Drop down, the next term is plus 1, and that's the end of the division. This is the remainder term. I hope that everybody's gotten this one. If you mess up the division, you're going to be totally screwed on the partial fractions because it's going to be totally different. So I hope that this is where you started off. So what I'm looking at then is the integral. The quotient part goes here, x squared plus 2x, and then the remainder part is 9x plus 1 divided by x squared plus 2x minus 3. All right? So this is the integral that I'm dealing with. And now we do partial fractions on that last bit. Any questions about this? I hope that you got the same quotient as I did and remainder. All right, now we do partial fractions on this part. So this part I write as a over, factoring this, I believe it's plus 3 and minus 1. I'll do it this way around. A on the plus 3. If you choose it the other way around, you'll get, everything will be slightly different. All right, when we make the partial, or when we make the common denominator, would you mind if I, since most of us already did this, this is sort of what it will look like when you make the common denominator and add stuff together, right? Once you do this enough times, you will begin to see how this generally goes. Okay, and then that numerator equals 9x plus 1. So I'd say 9x plus 1 equals, and then distributing a's and b's on the right, ax minus a plus bx plus 3b. And then rearranging these guys gives me a plus bx, and then minus a plus 3b. So my system to solve is a plus b equals 9, minus a plus 3b equals 1. Right? And then we got to solve this system. Actually, this one is convenient for adding the two equations together. I like to do that when we can. It's cute. If we add these equations, the a's cancel, and it'll just say 4b equals 10. Did I do this right? Anybody agree or disagree? No. I don't like that I'm going to get a fraction here. I thought anybody get something different?
I did it the other way and I got the same thing.
Yeah, okay. So b is 10 divided by 4. 2.5 if you like. I'm not afraid of the decimals if it comes to that. Or you could write a fraction 5/2. All right? And then a plus b equals 9. So that means a plus 2.5 is 9. So a is 6.5, I guess. Right? These are my coefficients. A little taxing when they're not whole numbers, but I'm sure we can handle it. On our tests and quizzes, I will make them so that they're whole numbers just because you're not using a calculator, and I don't want super weird. It's never going to be really weird, I suppose, but I'll make them nice. Okay, so we're pretty much done with the hard part, right? So my integral then, the quotient part was x squared plus 2x, and then my partial fractions part turned into 6.5 was the a, and the a is the one on top of x plus 3. So it's 6.5 over x plus 3 plus 2.5 over x minus 1, like that. And now we just do the integrals. The first two terms are ordinary power rule, 1/3 x cubed, and then 2 over 2x squared. And then the other two become natural logs. So it's 6.5 ln absolute value x plus 3, 2.5 ln absolute value x minus 1. That's that. All right. The end. So this is about as hard as these are going to get. It'll take you a few minutes to work it all out. And hopefully you don't mess up the details. Any questions about that? It's a, I would say, somewhat elaborate trick. Although as long as you don't mess up the numbers, it's not all that hard, I would say. You just got to keep the numbers straight. The numbers. All right, excellent. This is the end of this partial fractions business. Like I said, there's actually a few kind of related partial fractions tricks that I don't really want to get into. We could spend a whole week doing variations of partial fractions, which I'm not into that. All right, just the basics for that one. We got 5 minutes on the clock. I think we can talk briefly about the next section. The next section is called improper integrals. We are nearing the end of our little unit about integration tricks. We had the parts, integration by parts, and then we had the trigonometric integrals and the trig substitutions, which have their own sort of tricks that you have to remember, and then the partial fractions. Improper integrals is not exactly a trick for doing integrals, but this is about integrating. This is about doing integrals, I will say, up to infinity. What I mean by that is something like, well, we would write it something like this: 0 to infinity, something like 2 to the negative x dx. This is actually a classic improper integral example. Why it's called improper is because of the infinity up there, all right? Infinity, of course, is not a number, so you cannot do this like an ordinary integral, because an ordinary integral you would do the antiderivative of this and then plug in the two numbers, but there's no such thing as plugging in infinity. So we do need to discuss what this even means, but what it means, I would say, it means kind of what you think it means. That is, it represents the area under the curve of 2 to the negative x. Now, 2 to the negative x is an exponential function with a negative exponent. The graph of it looks like that. Sorry, I'm going to try and draw this better. Oh, yeah, that's better. Where this goes through 1. This is what an exponential function looks like with a negative exponent. It's like an ordinary exponential function which goes up to the right, but it's reflected horizontally. And then what this means is this represents this area. Now, I said 0 to infinity, so it's from here up forever to infinity, all right? That area is what I'm talking about. And the obvious, so we have 4 minutes left. The obvious thing to say is, well, that area is infinite, isn't it? Because it goes on forever to the right. So why are we even talking about this? Actually, what I hope to convince you of in our remaining 3 minutes is sometimes that area actually is not equal to infinity. So it's true that this area does go on forever as you go out to the right. Sometimes the area is infinity, and in that case we say something like the improper integral does not exist, or is undefined, or it diverges, sometimes we say. Just like some limits, they end up being infinity, and then you say the limit does not exist. Sometimes the area is infinity, but sometimes it's not. Even in an example like this one, this example, actually the area is not infinity. Even though the area goes on forever to the right, I think on an intuitive level you would say, well, then that means the area is infinite. Actually, it's not in this case. And this is profoundly weird, but check it out. Here's my 2-minute explanation. Specifically why this example is not an infinite area. This function is 2 to the minus x. 2 to the minus x, of course, is the same as 1 over 2 to the x. And if I were to graph this function at various values, let's say x equals 1, the value is a half, right? It goes here. At x equals 2, it's 1 over 2 to the 2. That's a fourth. The value is a fourth. At x equals 3, the value is 1 over 2 to the 3, which is an eighth, right? These values, of course, they get very small very quickly. It's always 1 over some power of 2, all right? Now, the area under that curve, check it out. What I'm about to draw is not equal to the area, but I can do, just like we do kids in calculus class, try to estimate the area by looking at the boxes, the area of the boxes. Check it out. What is the area of the boxes? These boxes, they all have width 1, but their heights are different, right? Just because of the way I drew them. The base width is 1. That means the area is actually just going to be equal to the height, because the area, of course, is the width times the height, but in this case, all the widths are 1. So these areas will just equal their heights. That means the first box, it doesn't look like it, but it has area 1, because the base is 1 and the height is 1. The next box, its base is 1, but the height is only 1/2. So the next one actually looks like this. Its height is 1/2. The next one, its height is 1/4. The next one, its height is 1/8, and so on. What's the total area of all the boxes together? Even though they go on forever to the right, actually their total area does not add up to infinity, because, check it out, we can stack them. Got to stack them all. The bottom one is a 1, right? And then I'm going to imagine like another sort of empty box with a 1. The next one stacks in with height 1/2, right? The next one stacks in with height 1/4, but if you think about when you stack them up, the next one actually fits in to fill half of the remaining space as 1/4. The next one is a 1/8, which again will fill half of the remaining space here. This is a 1/8, right? I will say ... It is a fact, they all fit inside this area, because each next block only fills half of the remaining space. All right, so all these areas, the total area here is actually 2. If you consider in the limit, as you add in all of these things, they will arbitrarily approach the top of this kind of ghost box, which the whole area then would just be 2. Okay, so what all of this means, this area right here, which goes out to infinity, not only, this area is not equal to infinity, even though it goes on forever to the right. In fact, its area is actually less than 2, because the area of these boxes is equal to 2. And so this area, it's not 2, but it's less than 2. So definitely not infinity. All right, we can actually find the area by doing some calculus. So that's what we're going to do next time. See y'all then. Let me know if you got homework questions. I'm happy to discuss.